Hi, in this chapter we're going to talk about the geologic cycle, Earth structure, internal energy, and plate tectonics. When we talk about geologic time scale, especially since we're talking about climate, it's difficult to tell how long things last or the general order time scales that we deal with. We had a little ice age about 700 years ago. We've had ice caps that extended to the United States about 10,000 years ago, and those are relatively small when we look at the whole age of the Earth. Earth's about 4.6 billion years old, so when we talk about relative time, it's difficult to tell that, especially when we look at things of like global warming, global climate change, and scales and sea level change and whatnot, because we've only been able to empirically measure these things with good certainty and accuracy for a couple hundred years, if that. So a couple ideas on how things change is uniformitarianism, the theory that Earth processes have been operating throughout geologic time. And basically the way that landforms are created are a combination of uniformitarianism and catastrophism. Brief, violent episodes, earthquakes, volcanoes, floods, or whatever, that combine with this uniformitarianism form the landscape. Localized catastrophes shape local and regional landscapes within the uniformitarian network, and that's some of the generally accepted, theories behind it. So what we see today is basically the result of billions of years of change. And so you can kind of get an idea as to where we are when we talk about dinosaurs. They died 65 million years ago. And you can see where that is compared to 570 million years ago. And this isn't a history class. This is more of a, this is a physical geography class, but I want to get an idea that what we're looking at right now is basically a snapshot of this geologic time scale, which is, to me, difficult to internalize at times. So don't worry about this, but you can just see an idea as to where we are now compared to where we've come from, the Earth, the history of the Earth at least. So you can get an idea that the previous slide mentioned the idea of strata, basically meaning you can see this is generally sedimentary rock where layers at the bottom are older than layers at the top. So we can get a relative idea as to age. And whatnot. So when we look at internal cross-section, we've got some indirect evidence. Direct evidence, lighter elements form the outer layer, heavier elements form the core region, like iron and nickel at the middle of the Earth, center of the Earth. And so you can see a cross-section, the Earth's magnetic fields with polarity. These days you have a compass, it points north, but not truly north. I used to work for I used to make maps for the military, so we had something called true north versus magnetic north, and something called magnetic declination. Throw in something called map north, and there's 3 different definitions of north. That magnetic north talks about the Earth's magnetic field. And this is just a cross-section of the Earth and its internal structure. The analysis of earthquakes, we know that waves travel at different speeds through different media. Sound travels at different speeds, underwater versus through the air. And so we have an idea as to where earthquakes occur, tectonic events occur based on how long it takes to get to a particular seismograph or location. And we also have isostatic events, isostasy. So if we have, we're adding something on top or we're taking something off. Think of it as a car. A bunch of people get into a car, it's going to sink. People get out, it's going to go up a little bit. Okay, so we have what we call isostatic rebound, that is changing the dimensions of the Earth or the complexion of the Earth. So we have some of these exogenic cycles, endogenic cycles, and geomorphology, which is the study of landforms and essentially their changes. So we have these different plates. The rock cycle, material is constantly being created and destroyed all over the planet. The Earth is divided up into these different plates, which move in different directions relative to each other. So in places where these plates or rocks getting destroyed, well, it's being created at other places. And we're going to show some really good examples of that. We have igneous rocks, which are fire formed from magma, and eventually lava. And so we have some of these igneous rocks, which are formed from volcanoes, or what we call spreading centers in other cases. We have sedimentary rocks, which are laid down in layers. So strata, these horizontal layers of material. And stratigraphy is the study of the sequence, thickness, and spatial distribution of these strata. And you can see examples of this strata or these sedimentary rocks, and metamorphic rocks, rocks that have undergone some type of change. So you can see some of these here. So we have plate tectonics. One of the things that people started to notice was that the coast of Africa and South America kind of looked like puzzle pieces. And it was noted in about the 1500s when we started making these large, small-scale maps of the Earth. But it wasn't until 1900s a German scientist named Alfred Wegener looked at the first scientific explanation, and he proposed it, but he didn't have a mechanism for it. And it wasn't until the mid-1940s where we saw research by the Navy where the seafloors were actually spreading that this really came to fruition. This whole idea of continental drift and plate tectonics has only been around for 70 or 80 years with undeniable proof of it. We've got mid-ocean ridges where plates are spreading apart, and then places like Cascade Mountains where they're colliding together, or the Aleutian Islands where they're colliding together and being destroyed. So it's kind of a zero-sum game. So we've got these spreading centers where rift valleys, and we do have rift valleys in Africa, Great African Rift Valley, where continents are being spread apart. Now, this movement is on the order of inches per year. And we have buildup of stress, so it might not move for years and then move 20 feet all at once. And that release of energy is what we call an earthquake, which we'll talk about next chapter. But it wasn't until the 40s where we started to get the idea as to newer rock was closer to these centers, older rock was further away. So we started to see this mechanism for Wegener's theory. So we have subduction, and then he proposed the idea of all earth and all seas, and the continents are still in motion, and it wasn't until later where we started to figure out we've got these different plates. We've got a Pacific plate, we've got a North American plate, and these move in different directions relative to each other. Okay? And like I said before, on the order of inches per year. We have a little plate off the coast called the Juan de Fuca plate, and I'll show all these here in a little bit, versus the North American plate. And you notice parts of California are on the Pacific plate, while most of North California is on the North American plate. And this is what we call the San Andreas Fault right here. There's a lot of other smaller subfaults here. A fault is just a break in the rock where we have movement, because it's not going to crack and break nice and easily here, but you can see, San Francisco's right on this fault here, but Los Angeles and San Diego are on one side of the plate, moving in one direction relative to the rest of North America. It's really interesting. I believe up in University of California, their football stadium is literally on the fault. In the last 10 years, they've undergone basically a retrofitting to account for that. So you can see these plates. And like I said before, this movement is very, very minor. The Himalayas are still being uplifted as a result of a collision from the Indian subcontinent. It crashed into Asia about 60 million years ago, and the result is the Himalayan mountains and the plateau. Okay, so we call this subcontinent, and it's literally just crashed right in, and this is the result of that collision here. And so you can see we have these spreading centers. We have divergent plate boundaries where they're moving apart, convergent where they're moving into each other, and transform where they're moving past each other. So that example I showed before of the San Andreas Fault would be a good example of that. And then we have hot spots where basically we have an upwelling of magma, that's not near a plate boundary, but we have magma there, and we have tectonic activity. And a good example here is Hawaii. In 2018, we have these Hawaiian Islands. It's nowhere near a plate boundary, but it's a result of this hot spot. Yellowstone National Park is another result of this. And then we've got Iceland, and some of Iceland is going to be at a hot spot. A lot of it's going to be at this divergent plate boundary. But you can see these hot spots here at Yellowstone, Hawaii, nowhere near a plate boundary. Okay. And so you can see some of these islands here. There's a long island chain, of which the Midway Islands, if you're a history buff, Midway Islands are part of the Hawaiian chain, but it's this long stretch of islands and what they call seamounts, basically islands that don't get above the surface of the earth, surface of the water. But you can see these boundaries right here, okay? And you can see these plate boundaries. We've got the Eurasian plate, South American plate, Nazca plate, Juan to Fuca plate that I mentioned before, and they're just moving in different directions relative to each other. These are some active areas of volcanoes, plate tectonics around this particularly focuses on the Pacific Ring of Fire here. In 2004 we had that big earthquake in Indonesia, occurred right here off the coast of Banda Aceh. But you can see a number of other places. Mount Vesuvius over here in Italy, Mount Etna in Italy here. And then we have tectonic activity over here in Turkey, South America volcanoes, all around this, and we've had some in New Zealand. This was interesting here. This is the hot spot, or this is a divergent plate boundary. These are my pictures from Iceland. And this is literally where the earth is being split and magma is coming up to take its place. This looks a lot like Yellowstone Park, but this is in Iceland. There's a geyser here. The name of it is actually geyser, Geysir, where they get the name geyser. And this is called Gould Falls, where basically the country of Iceland is literally being split apart right at this area here. And this is being fed, I'm not sure, there's volcanoes in the middle of this country. Being fed by glaciers, miles away. This is literally where one side of it is on the Eurasian plate, the other side is on the North American plate, being split apart. Then you can see from 1991 to 96 the intensity of earthquakes. I believe you're going to have an exercise where you utilize the USGS website. You'll notice that most of these occur at plate boundaries, but some of them don't. We have earthquakes in Oklahoma these days. In mid-2000s, we've got earthquakes in Oklahoma. We've got earthquakes in Wyoming that don't occur at plate boundaries. So those are important to understand and realize. Charleston, South Carolina, 1886 had a major earthquake. So there are fault zones outside of these plate boundaries, because like I said before, a fault is just area where rock is moving past each other. It's most likely to occur at a plate boundary because we do have that movement from these internal processes, but these stresses and strains of these rock will cause can cause earthquakes anywhere. And then you can see Hawaii here with the hot spot, and then that's about it for